Okay, just to recap from yesterday, largest independent set in dense graphs is 2 log n. Sparse graphs, it's slightly different. Can we find it by fast algorithm? Well, you can. It's fairly easy to implement and analyze the borderline a trivial algorithm. It's a version of a greedy algorithm, finds an independent set of half optimum. I was planning to show how this works. Let me not do that. It's but indeed the idea is very, very simple, and you can find also it's in some of the textbooks. Okay, this was observed by Descartes 1976, and he said, well, the algorithm is so simple, surely we should be able to do better than that. But this is still open, and this is embarrassing. Embarrassing because the algorithm that works is super trivial, but nothing better seems to work. And it's at the same time, of course, at that point, it's natural to conjecture that this problem is hard, but we can't show that either. It wouldn't be ridiculous to show that this problem is hard on average. For random P not equal to in P version on the random structures makes sense. And there are results of that kind. There are results of the kind that you, unless P is equal to NP, you cannot solve certain optimization problem in the random structures. Lattices are example. So there are some examples in cryptography, but not this one. Okay. Sparse graphs, same story. And in fact, the optimality gap here is also 1/2. So greedy gives you independent sets, which is roughly 1/2 optimum. And I'm not going to extend it like this because I'm afraid I will make another mistake here. And nothing better is no. Good or not so good, but that's the fact. Another class of models for which I wanted to introduce yesterday, but I didn't have time, are spin glasses. All I will say here is that there is a very similar story in the sense that it's an optimization problem on random structures. There is optimal value. It's pretty well understood. There is the algorithmic advances that give you some value. Generally, though, that value falls short of the true value. And somewhere in between, there is a version of the overlap gap property that I've described yesterday. I will focus on independent sets because that's the one that's the simplest to discuss. Yes. Right. Okay. So let me go to the slide where I have independence. So, okay, that's the model. Let me just describe the model. It could be many things, but let me describe something concrete. Okay, so here's the model. So we consider a random tensor. It's a little bit of a dense slide, but so let me walk you through that. We consider a random tensor. So it's n by p tensors. If p is equal to 2, that would be just a matrix. Every entry is standard normal. We consider the following optimization problem. We optimize over the binary vectors of plus minus 1 to power n. This is our optimization space. What's the value for each sigma? It's just the inner product of tensor as a vector with the outer product of sigma with itself p times. Or put it differently, just look at the following sum product. Entries of the tensors and corresponding products of the sigmas. This is the what's called the spin glass model. Maximum value of this is called the ground state. It is known upon proper normalization. It is known what it is. So you have to normalize it like this. Then it's a constant. This constant is known, by far non-trivial to compute. It's an implication of the Parisi ansatz and so on, but it's known. Nicely, though, is p goes to infinity, this constant trivializes to something very simple, square root 2 log 2. The square root 2 log 2 comes from the extreme value of the independent Gaussians. All of this is sort of besides the point, though. Okay. it is a mean field model in the sense that all of the tuples are present here. There is no graph structure here, or the graph structure is complete. It's a graph structure is a complete hypergraph on with the cardinality P. But there's no interesting graph structure to discuss here. That's not where interesting things happen. Let me go back to, all right. Okay, I was here. All right. The algorithms that that work, and the best known algorithms that work for spin glasses, are by far non-trivial. Unlike the greedy algorithm here, are by far non-trivial. It's a fairly recent development, including Ahmed and Andrea Montanari and others. So they get you to certain value, but not all the way to optimality. But so now let me turn my attention to a class of algorithms that it so happens encompasses both the greedy algorithm and the algorithm that used for the spin glasses, and pretty much any other algorithms that we have seen when we see this phenomena. Formally, this is the class of algorithms we'll discuss is the low depth Boolean circuits. I'll define what it is now. Loosely speaking, you can think of it as low degree polynomials, but I want to stick with circuits. So Boolean circuits is one of the most favorite class of algorithms considered by theoretical computer scientists. It works as follows. So a Boolean circuit is an algorithm. As an algorithm, it needs to be able to map inputs to outputs. So it needs to map, for example, graphs to decisions, like concrete independent set that you want to construct from the graph. Now, because the graph has adjacency matrix representation, you can think of it as the bit string with the n/2 length. So the input we will think, when we think about graph as input, we'll think about the element of this Boolean cube. Right? Boolean circuit will be a particular mapping that maps every such bit strings to the bit strings of length n, with the idea that these bit strings, the output bit strings, encode independent set. Okay. All right. So what is the class of algorithms and that we consider here? The class of algorithms called Boolean circuits are constructed by considering a certain directed graph. Here it's a directed graph going from down up. So it's upward direction. All intermediate nodes have associated with logical gates negation or an n, except for the bottom part. And including the top part. So the way, once you have such a graph, you can take any input bit, put any bit string input here, pass it along this graph, and get something here, right? So any graph, and in particular any bit string adjacency matrix associated with graph you put in here, will induce some kind of a bit string here that you hope is a good one. You hope that this bit string represents independent set. You hope this independent set is large. You hope it's large always for at least for random graph. Okay. All right. Any questions about what's a Boolean circuit? I guess I didn't say explicitly the meaning of these logical gates, but the meaning is that once you have a certain collection of inputs, all of these inputs are 0, 1 type, and you have the particular operation here like OR. So you take the OR of this input, and that gives you another bit, 0 or 1. So once you start in here, you have a collection of zeros and ones here, which are induced by this logical operation. No questions. All clear. Okay, good. So a bit of a background. There's several parameters associated with Boolean circuits, but the two that we will focus on are the following. First is the size, which is the number of gates, the number of nodes that you see in this network. And the second is the depth, how many layers you have. And you can play with these two parameters and try to see what's the expressive power of such Boolean circuits, what kind of a complex problems they can solve. For this discussion, arbitrary fanning is allowed, but of course there's lots of results, discussions, and so on with the restrictive fanning. Not in here. Arbitrary fanning is perfectly fine. It turns out that if you only limit the size of the Boolean circuit, then you're hardly making any progress, in the sense that poly-size Boolean circuits are as powerful as any Turing machine running in polynomial time. This is not exactly true. There's some caveat there, but for non-experts like me is good enough. There's some discrepancy, but it's really not important. So if you only bound the size, if, for example, I want to argue that there's no polynomial size Boolean circuit that solves independent set problem, good luck to me proving that, because that would imply P not equal to NP. However, if you in addition bound the depth of the Boolean circuit, then you can say something more concrete. And in fact, one of the biggest breakthrough in this area was the work by Hastad, who said that if you bound if you have a polynomial sized Boolean circuit and you bound its depth by some constant log times log n divided by the log n, such Boolean circuits cannot even solve a borderline trivial problem like parity. Parity is just a problem where you have a bit string and you need to decide if the number of ones is even or odd. Right? Turns out the Boolean circuits of that size, the polynomial size and bound on the depth, cannot do that. Parity is a trivial problem. Annoyingly, though, trying to prove similar bounds for interesting problems like independent sets or its mirror image like clique turned out to be pretty difficult. But there was a series of progress, and I'll just tell you at some point, I'll tell you, I think I'm telling you here, the state-of-the-art result that says that polynomial size circuits that compute cliques of a particular size, it happens to be on a random graph, but slightly different regime, that doesn't even, this part please ignore. It just says that poly-size circuits computing cliques have depth, which is nearly what you get from parity, just a little smaller. Log n divided by log n, then there is a growing factor here. That factor is the size of the clique or independent set that you look at. All right. So, and that's the state-of-the-art result by Rossmann, and it was quite justifiably quite a breakthrough, a very important result. Okay, all right, and we'll come back to that. Another kind of a lever that you can play with is as follows. Let's say we only look at circuits which have a depth which is constant. These are called AC0 circuits. So we only look at the constant size circuits. Of course, constant size makes this even like more restrictive. Then the question is, okay, can you have a polynomial size circuit solving your problem? Or if it's not polynomial size, how large it needs to be? It's called the size depth trade-offs type results. Rossmann's result implies exponential of log squared lower bound on the number of, on the size. And size is the number of gates for the clique. Okay, so we will come back to that. Right. Now, what is the relevant to us? It turns out that both the greedy algorithm and the algorithms achieving the best values for the spin classes can be coded as circuits of polynomial size with a constant depth, as AC0 circuits. So those are special cases. This is not, it's not a trivial observation, but it's not too deep. So one just has to realize that the type of computation that are involved in these algorithms can be coded as polynomial size circuits with a constant depth. Okay. All right. Good. So far, so good. Let's continue. But please stop me if you have any questions. why circuits of the limited size and limited depth interesting? Because they exhibit a certain stability property that will be crucial for our negative result. And once instantiation, a very important instantiation of the stability property is the so-called linear Mansur-Nissan theorem of 1993. I don't remember exactly the, 1993. Let me share with you this results. It's really one of the most, next to Hastad switching lemma, is probably second most important result in this area, in the area of Boolean circuits. Unfortunately, for the formal understanding of this theorem, one needs to be familiar with the Fourier analysis on a Boolean cube, which I don't expect you to be, but if you are, then that's the language in which this is stated, but I will paraphrase it in more sort of humane language shortly. To start with the formula, it says that for every circuit with a size S of n and depth P of n, if you hit this circuit, if the input is uniform random on the bit string, admittedly, I did 0, 1 to the end here, but we had n choose 2 before, so I apologize for this discrepancy. This is the input size to the circuit. It so happens the sum of squared Fourier, so-called Fourier coefficient associated with monomials of order bounded like this is vanishing. Okay. Now, first, what is this term d sub n? This is a log of the size to the depth, to the power of the depth, order of depth. There's some constant here. All right. So, all right. Here's an informal interpretation of the statement. As it so happens that, okay, so just to remind you what we're dealing with, we have a circuit. Let's think of it as a function from 0, 1 to the, let me write capital N here because it's, for now, let's look at the, let's look at this as a, let's think of circuit as a mapping as with the images, not the bit strings, but any values in R. So it's a univariate circuit. It so happens that you can always, for any input X, you can always expand it as a polynomial with some kind of a coefficients alpha S, X sub S. In what sense? So S goes through all subsets of n elements from 1 to n. Alpha S is some number. This is the Fourier coefficient. X sub S is just a product of variables X sub I in the set S. Right. The largest, so therefore the degree of the function C that encodes this is at most capital N. Right. It takes a little bit of work to show that indeed any such function can be encoded like this. This is linear algebra on a Boolean cube, not too deep. So the deep part of the linear Mansur-Nissan theorem says that, in fact, if we take the approximation of this polynomial, where we only look at the sums xs, where cardinality of the set is at most this number d sub n, this is good enough in some sense. That's the idea. So drop all the monomials of too high power, you still get a pretty good approximation, right? If this function is indeed a low depth circuit. Let's get some assessment of what kind of a coefficient sizes we need to drop when we do that. Let's say our circuit is polynomial size, depth log n over log n. What is the log size to the order depth? Well, it's log n to the alpha, but alpha is going to disappear to the and the depth beta log n over log n, and then simple calculation shows you that this is n to the beta. So if beta is less than 1, then the degree is sublinear in n. Okay, all right. So if it so happens that you have a Boolean circuit with a depth like behaving like this, and beta parameter is less than 1, then you know that this Boolean circuit can be well approximated in some sense by a polynomial with a sublinear degree. And we would like to take advantage of that. Any questions? So far, it's good. All good? All right. I'm going to 12:30, right? So, okay. All right. Now we will collect everything we have learned so far and synthesize how geometry conspires against algorithms. So this third part, which is the basically now we're collecting the harvest, so to speak, of what the things that we planted yesterday and now, this by itself will have two parts. Slightly easier part that will not make reference to Boolean circuits, and more complicated part that we will need to do in order to say something interesting about circuits. So let's put circuits on the side for a moment, and just come back to what we have discussed yesterday. I want to remind you briefly and quickly the landscape result that we have almost proven yesterday, nearly proven yesterday, except where we did it for dense graph, but I want to do that for the sparse graph. So let me remind you what it is. We've looked at the series of graphs G of t, which each of the graph looked in distribution as a, well, now it's going to look like a sparse Erdős-Rényi graph, and we're going to do that interpolation for n choose 2 steps. So we have our graphs here: graph 1, graph 2, and so on. Graph this is G1, this is G2, and so on. This is G n choose 2. Yesterday we've realized that the following property holds. If you look at the independent sets which have cardinality at least some factor, well, we worked with 1 over 2 times optimality. And if we pick such an independent set of this cardinality, 1 in here, and 1 in here, and 1 in here, and anywhere in between, and take any two of such independent set, but now let me focus on the ones that, okay, I started from 0, so let me be consistent. 0, 1. So take this is I0. Take any one in between. This is IT. So you have one independent set. This is I0. Another independent set. This is IT. They can look like this. They can look IT. They can look like this. They cannot look like this. I0 here. This is IT. Intersection size of intermediate range is not realizable. But also, if the second independent set came from the last graph, then this picture, so for I0 and I n choose 2, this picture is not possible. And then there was another diagram that I will also rely on that basically said that yes, as t goes from 0 to n choose 2, you can, at the beginning, you have large intersections and you have small intersections, but starting from a certain point, only small intersections are realizable. Large intersections are not possible anymore. Okay, that was from yesterday. Just wanted to quickly remind you of that. Now we're going to hit this picture against algorithms, a particular class of algorithms that we will call, for the lack of a better term, stable or noise insensitive algorithms. For the purposes of this meta theorem, this is an informal statement of the theorem that can be formalized in different instantiation for different models and different implementations, but informally goes like this. First, and what is an algorithm? For the purposes of this theorem, algorithm is just a mapping from graphs into decisions, graphs into independent sets, for example. Yep. Okay. We will say the algorithm is stable if it has the following very intuitive property. A small change in the input results in a small change in the output. So that, for example, if I have a graph and I just update this graph with one edge, delete this edge if it was there, add an edge if it was not there. And then I see how much my algorithm changes its output. So if my algorithm did not drastically change its decision, then we call it stable. Of course, drastically, a little bit, too much, and small change, large change, all needs to be quantified. That's for sure. But informally, that's the idea. Turns out that the noise insensitivity is kind of a right language to talk about that for the reasons to be clarified shortly. A very simple idea reveals that this picture cannot coexist with the stable algorithms. If the algorithm is stable, it is hopeless against producing independent sets of this size for this interpolated sequence. And the reason is very simple. It's here's a proof by picture, and I will reproduce this proof on the board in sort of real time, because it might not be very well. Pictures, they're small and not very dynamic. So let me just describe what it is. Okay, so we have a graph, starting graph. We have an algorithm, and that produces some independent set I0. Let's think of it as a dot. This is my first solution. Then I look at the next graph, G1. G1 differs from G0 by one edge. Remember, the way it was the resampling was done was resampling one edge at a time. Okay, if my algorithm is stable, that means I1 symmetric difference with I0 is small. I'm not going to say exactly how small, but should be small. So there's a little jump here. This is I0, this is I1, so it's small. And then I keep doing this. G2, so I move like this, like this, like this, and so on. But what do I know? I know that, well, in the end, I need to produce an independent set of size and choose two. In the independent sets of large size in the final graph, right? My algorithm is stable, so it goes in these kind of small steps and ends in here. However, the picture there says that every intermediate independent set differs from the original one, either just a little bit or substantially. And there is intermediate ranges which are not realizable. That means that either it has to be within this ball, which has a radius μ1, or it has to be outside of the even larger ball with a radius μ2. But that means that at some point, this algorithm had to jump. It could not walk comfortably in between. It's like walking between one peak of the mountain and another peak of the mountain. Not possible. This is not possible. There should have been a jump here. This is an extensive jump. This is order n jump, as it turns out. It's all to be verified. And therefore, if the algorithm is stable, continuous, it cannot achieve that. And that's pretty much the whole idea of the entire proof. Let's try to use this proof to show the failure of Boolean circuits of whatever size and depth we can. And unfortunately, this, is this an abstraction to Boolean circuits? Unfortunately, the direct application of the Boolean, of this picture to Boolean circuits and showing the failure of the Boolean circuits fails, no pun intended. it fails because, all right, what do we know about, right, it fails, so more work needs to be done. But let me first, I guess, share the main result and sort of main conclusion. So if we consider circuits, all circuits of a particular size, a particular depth, and let alpha be the approximation factor. All along, I've been discussing factor 1/2 plus 1/2 root 2. It turns out that that can be brought all the way to 1/2 in a more complicated version of the overlap gap property that was invented by Alex Wine in 2020. So it's a multi ensemble OGP. Sorry for the mouthful here, and that I did not describe, but it involves, instead of looking at pairs of independent sets, looks at the multiples of independent sets. It's just too complicated to state, but morally it can be extended. In that case, this holds all the way up for all independent sets up to 1 plus epsilon, or half 1 plus epsilon optimality. So anytime independent set is larger than this, it exhibits a version of this interpolated sequence I've described. Back to the circuits. So here's the claim. There's two parts in this claim. Take any approximation factor larger than 1/2. Take any epsilon. If the circuit has depth at most that much, this is the similar scaling that the parity we've seen in parity, then this circuit should have a super polynomial size. So that's the kind of a failure of the circuit. That's one implication. If in addition, the same setting, but if in addition you require that the circuit has a size at most a constant p, then its size itself should be nearly exponential, but in n to the beta for some constant beta. Okay, so that's the main result. Just to briefly remind you from in comparison, this does improve the state of the art that was achieved by Rossmann and collaborators. There's some extension of this by Razborov and Lee. Log depth, the depth goes from something smaller log n over log n to the genuine log n over log n. That's the improvement. Most dramatic is the improvement in the size. Their size lower bound is exponential in the log squared. Our size lower bound is exponential. Unfortunately, a big caveat here that I have to disclaim is that their version of the circuit is for the decision problem and not for the search problem. And there is a difference between the two. And that would be nice to actually bridge this as well. There's some partial progress in this direction, but I will only offline. I'll discuss that. Any questions so far? And the map and the sort of and the roadmap to proving this would be doing this picture versus this picture, except for it doesn't work direct. We have to do a little bit more work. So let me discuss it. So I said linear Monson-Nissan theorem tells you that Boolean circuits can be approximated by low degree polynomial. But what does it mean, right? What does it mean they can be approximated by low degree polynomial? As it turns out, basically it says something like this. All right, so you have a circuit. It inputs a Boolean string into some decision. Right? So the stability or noise insensitivity is in reference to the following things. So you have an x from 0, 1 to the n, chosen uniformly at random. Fix any coordinate I among the n coordinates, and consider the flipping of this, resampling the coordinate I. So xi is obtained from x, let me call it x minus I, something like this, is obtained from x by just resampling that coordinate only. And then you look at the cx, You see how much of a difference that results. Linear Mason-Nissan theorem tells you that the expectation of this difference in some absolute value is little, is small. So it's a guarantee on expected change of your of the output of the circuit. What it translates to in this picture, it's, as it turns out, with a little bit of work, it translates into saying that in expectation, all of these jumps are small. In expectation. But that's not good enough, because it suffices to have one exception from that, and we fail, because in expectation there's n choose two steps. Maybe all but one were small and one is large. That's consistent with expectation bound. So that by itself does not work. Let's see. Nevertheless, let's see what this leads to. So, okay, we have an interpolated sequence. So this is a proof map. We have an interpolated sequence. We apply the circuits. Circuits presumably produce independent sets, presumably of large size. Okay, we'll look at the sequence. Right? What we know, as I said earlier, is that what we know that in expectation, this difference, I wrote it as L2 known difference, but you can think of it as Hamming distance. Doesn't change anything. In expectation, this quantity is small, appropriately normalized, and so on. In particular, it will be smaller than some constant from the OGP. So that in expectation, we have that, but we need it for all steps. The fix turned out to come from the large deviation analysis. With a little bit of work, or not a little bit of work, it's actually quite a bit of work turned out, one can show that all of the steps are small with probability, admittedly not too large, but lower bounded by this term, exponential, with some constant delta that we can control. And dn, I'll remind you what dn is. dn is log size to the power, which is depth. And the interesting regime, it's going to be something like n to some beta, and beta is going to be less than 1. That can be arranged. All right. So, so we can show that, in fact, this entire path is stable. It is kind of consists of only small jumps, but that happens with small probability, but small but controllable probability. On the other hand, we know that when this happens, we cannot have that picture. So this picture should happen in the exception event of that picture. The OGP, in other words, it should be in the regime where this interpolated sequence of graphs was not exhibiting overlap gap properties. But that's controllable. It so happens that the violation of the OGP happens with exponentially small probability. That means that this bound on the stability of this path should be smaller than exception probability of the OGP. Okay. And then the rest is just algebra. Okay, plug in the numbers. For example, let me actually do that for the, I didn't do that. Plug in the numbers. And then you get what you want. Let me do that in this easiest setting, when we bound the depth. When we bound the depth of this circuit by constant. So it's not a very complicated algebra, but all right. So parameter dn is log size, log s to the p. By assumption p, the depth parameter is constant. With what we have from here is x minus delta, some number that we control, dn has to be smaller than exponent with some other constant times n. That comes from the violation of the OGP. That means that the d sub n has to be at least as large as c over delta times n, and dn is here. So that means by raising to the power 1 over p. This has to be at least p over delta n to the power 1 over p. And that means that size has to be at least exponential, dropping the constant terms, exponential of something like order n to the 1 over p. And that's the argument to show that this is the bound on the size. In particular, the size has to be at least exponential. Okay. All right. So the most difficult, one of the most difficult technical part in this was actually completely independent of circuits or anything else. It's dealing with this large deviation event. And it's based on the following theorem. I would like to share this theorem or lemma with you because first, we have not seen it in this form anywhere, but we believe it must probably be known. And also the proof was annoyingly complicated. There should be something simple. So now for this part, you can forget safely about anything about I said earlier and consider the following setting. We consider Boolean cube, 0, 1 to the n. Think of it as a graph with a natural adjacency structure where two nodes, two bit strings are adjacent if they differ by 1 bit, so Hamming distance. Let E be any subset of edges in it, and let little e be the fraction of the edges. The total number of edges 2 to the n minus 1 times n, that's because of Hamming distance business. So the fraction of the edges is this total number of edges divided by the total number of edges in the set E by the total number of edges. Consider a random walk which is constructed as follows. Starting point is chosen uniformly at random, and you run this random walk for t times. And you ask, what is the likelihood that my walk never touches edges, crosses the edges from set E? That's a large deviation event. It turns out that the probability is at least, we need the lower bound on this large deviation event, is at least 2 to minus capital T times E. We need not asymptotic large deviation. Typically, large deviation lower bounds are of asymptotic nature. So asymptotically, Zen goes to infinity and so on. We need the concrete one. Asymptotic is not good enough for us. In concrete one, we get is this. Annoyingly complicated to prove, not too crazy, but annoyingly complicated to prove. But it feels like this kind of a statement should not require proof. It should be some kind of the book kind of a from the book statement, but we couldn't find. So if you know something that resonates with, if you know something which is similar, do let us know. Let me close with some questions. I started this whole thing with independent sets. Sorry, it says cliques here, but it's the same thing. Independent sets in dense random graphs. There's a failure of algorithms, this factor 2 gap. It would be nice to show that this factor is not bridgeable by something like low depth circuit. We can't do that. We only did it for sparse random graphs because for dense random graphs, the exception event, for the OGP not to happen, it's rare, but it's not too rare. Its exception probability is not sufficiently small for the circuit bound to kick in. So that was a failure. Another direction is indeed connect the decision versus search bounds. So to remind you, Rossmann and others, they show the failure of circuits for the decision problem, not for the search. And well, the third one is kind of a generic. Are there any evidently hard problems, but not exhibiting overlap gap property? In other words, to what extent overlap gap property is the right theory for the hardness? We see that evidently that's the case, but only evidently. So the lack of evidence is not an evidence, or should I say, the absence of the evidence is not the evidence of the absence, right? So it's we don't know. Good, thank you, and I apologize for abusing your time for a few minutes. Yeah. Yeah, yeah. And God knows, yeah. Yes. So the as it turns out that if you look at the particular heuristics that was sort of promoted by physicists called the survey propagation that you know. So if you look at the survey propagation, which is a kind of a belief propagation on steroids, so to speak, this algorithm, if you consider implementation of this algorithm in only bounded many iterations, then it can be coded as can be coded as local algorithms. As such, can be coded as vectors of IID. As such, it can be coded as low-depth circuit. When we shared this result with physicists, they sort of trashed. No, I shouldn't say trashed, but they said no, that's not a full deal. You need to run the survey propagation for many iterations before it actually converges. But then, and we tried, but it didn't work. But then I mean, Koja Oglan's student, Sam Hattering, he put us out of misery by proving that it doesn't matter how many rounds you do the survey propagation, it will fail, but not using this method. He directly analyzed the performance survey propagation. So that's the story. Yes. Are actually stable? Yeah, good question. So naturally, lots of algorithms that we can think of, sophisticated algorithms like maybe based on semi-definite programming, linear programming algorithms, all kinds of, they don't need to be stable. That's by no means I want to make this statement. It so happens though that the algorithms that were successful in the random structures that we analyze, they happen to be stable, but only evident. There was some recent exception to that, which is there's a certain class of algorithms that was considered for the discrepancy analysis that was invented by Nikhil Bansal. That's many of you are familiar with that. It's an algorithm that solves the discrepancy problem. In particular, there's a version of it which is the perceptron model. That algorithm, and it's a version of it which is joined with Spencer, so Bansal-Spencer algorithm. We tried to prove that it's stable. It's probably not stable. We probably can prove that it's not stable. Nevertheless, that algorithm itself exhibits overlap gap properties in the sense that because it's an online algorithm, it exhibits a certain structure that itself has overlap gap properties. So we don't need to stick with the stable algorithms. We can go beyond that, online being the case. But easy, but solvable. Yes, one of the this is kind of a elephant in the room that sort of annoying people. These are the models which can be solved by Gaussian elimination. So, for example, if you look at the random instance of the mod 2 system of equations with mod 2, you can solve it. You can see if there is a solution by Gaussian elimination, but it does exhibit this clustering structure and OGP. Yes. It Uh, Possibly, but the algorithm, which is the Gaussian elimination, is not stable. It's not going to be stable. But GF2, so that to demystify a little bit what's going on there with the clustering and so on, the reason that GF2 exhibit the version of OGP is because these are codes. And codes are sort of an extreme form of clustering. There's solutions which are isolated points with no points nearby. That's why they are codes. And so they have exhibit this strong form of clustering. Nevertheless, you can, if it's a linear code, you can solve it by Gaussian elimination. So that's that. That's the elephant in the room. Then it's killed. Then it's killed. Right. Exactly. Then it's back to this, I think. Right. So you know what Ahmed is saying, that consider this random system of mod2 equations where your goal is, let's say it's not satisfiable. There's no solution. You can verify that easily by running Gaussian elimination, but you want to find a solution that maximizes the number of satisfied clauses, some satisfied equations. Then it's back to the, it seems hard, probably exhibits OGP. I'm not sure it was verified. And as such, it's abstraction to all kinds of algorithms like circuits. All right, thank you.